Happy morning all. In this lecture, we are going to derive numerical aperture and acceptance angle of an optical fiber. Okay. So before going to derivation, we have to know what is numerical aperture and acceptance angle. In an optical fiber, we know that, just consider, this is the core of an optical fiber and center axis, and the cladding will be there. The refractive index, let us take, the core is N1 and the cladding is N2. N1 should be greater than N2, that is, the core should be more denser than the cladding. Okay. Now, what will happen when a light enters into an optical fiber? Just consider a light ray is incident on an optical fiber with an angle of incidence I. It will, okay, so here the refraction is from rarer medium to denser medium. So the light is entered from rarer medium to denser medium. So the refractive index of air, let us consider N0. Now it will bend towards the normal. So what will happen? It will bend. Actual path should be like this. It bend towards the normal. Here it will hit like this and gets reflected. What is the condition for here to get total internal refraction? Okay. Here, when a light hits here, this is from denser medium to rarer medium. The light is hitting here in the interface between denser medium to rarer medium. Obviously, the light will move away from the normal. But here I want total internal refraction, so the angle should be greater than critical angle. Okay. So now what will happen if you increase the angle of incidence here? Okay, the angle of incidence inside the optical fiber will decrease. Okay, it will keep decreasing. If you increase here, it will further bend. Okay, it will bend like this. So now you can see the angle will keep decreasing. So there is a maximum angle of incidence at which, okay, internally it will be equal to critical angle. If the angle of incidence increases further, it will be less than critical angle, so the total internal refraction won't take place. So that maximum angle of incidence we are calling acceptance angle. Okay, so above this, if you increase the angle of incidence, the light won't get total internal refraction inside the optical fiber. And using that maximum angle of incidence as an acceptance angle, okay, so theta A. And if I do it as a three-dimensional, it looks like a cone. Okay, this cone is called acceptance cone. And that total cone angle is called acceptance angle. Okay, this theta A is half acceptance angle. Now, when a light enters into an optical fiber, only the light which is coming within this cone will be transmitted. That means the total internal refraction will take place and the light will be transmitted. If a light hits above this cone, okay, angle, what will happen? Inside, it will be less than critical angle and it won't get total internal refraction. The light will be lost. Okay. So now we are going to derive this acceptance angle. And what is numerical aperture? Numerical aperture is light collecting capacity of an optical fiber. Just consider, okay, so now if you expose this optical fiber in front of a powerful source, okay, not all the light will be transmitted, only the light which is coming within this cone will be transmitted. Okay, so only those lights are getting total internal reflection. So now the light collecting capacity depends upon this cone size, cone angle. So numerical aperture is light collecting capacity and it depends upon this cone angle. Okay, now if the cone angle is higher, okay, the more light will be collected. Both the things we are going to derive now. So for this, I'm doing another diagram. Let us take an optical fiber. Okay, the cladding, and this is the axis, and the refractive index of the core, let it be M1, this is M2, and this let it be M0. Okay, refractive index of air. Now, a light is incident on our optical fiber with an angle, okay, let us take θ1, and it will bend, okay, it will bend. Instead of going like this, it will bend and falls on the core cladding interface. For convenience, now let us consider it is above critical angle, it is getting total internal reflection. Okay, now the angle of incidence okay, so this is the normal. Let us mark the point A, and inside the core cladding, okay, B, and let it this point be C. Now this is the θ1 is the angle of incidence in the air core, and angle of refraction, let it be θ2, and inside, okay, the angle of incidence between the core and the cladding, okay, let us take θ. So using this diagram, we are going to derive numerical aperture and acceptance angle. In a simple way, so let us start. Apply Snell's law at A. See here, at A, the left hand side is air and the right hand side is core. The refractive index is N0, N1. So we can apply Snell's law. So sin theta I, angle of incidence, θ1 by sin θ2 equal to, okay, the ratio between the refractive index, so N1 by N0, where N0 is the refractive index of the air, which is equal to 1, so that this equation can be rearranged. Okay, so sin θ1 equal to N1 sin θ2. Okay, now just think of this triangle ABC. If you see a triangle ABC, if you add theta, θ2, and this is 90 degree, so the total angle will be 180 degree. So θ2 should be 90 minus theta. Okay, so from triangle ABC, we know that. Okay, so θ2 equal to 90 minus theta. Apply this in equation 2. So sin θ1 equal to M1 sin, instead of θ2, I am putting 90 minus theta. Sin 90 minus theta, okay, is equal to cos theta. So sin, you just convert this into cos theta. Okay, now And we can rewrite cos theta in terms of sin theta. Okay, I want in terms of sin theta so that it will be easy to compare on both sides. So n1, we know that cos theta equal to 1 minus sin square theta to the power 1 by 2. Okay, which is derived from sin square theta plus cos square theta equal to 1. So let it be equation 4. Okay. Now let us apply Snell's law at B. Okay, so we are going to apply Snell's law with a condition. Okay, let us consider this theta. Okay, this theta is just a critical angle. So instead of theta, I can put theta C. Okay, when this becomes critical angle means now this theta 1 should be equal to the acceptance angle. Okay, as I told earlier in the beginning, okay, if you keep on increasing the angle of incidence at one particular angle of incidence, this theta becomes or equal to the critical angle. Okay, so we are just taking that condition that when angle of incidence is equal to the acceptance angle, this theta will become critical angle. So at this condition, let us apply Snell's law. So what will happen here? If this theta is equal to theta c, this reflected ray will just grazes the surface. Okay. If the angle is above this, it will get total internal reflection. So using this condition, we'll apply Snell's law at B. So when theta 1 equal to theta A, that is acceptance angle, and theta will become theta C, critical angle. Okay, so now apply Snell's law at that point. Okay, so here sin theta C by sin 90 degree equal to n2 by n1. Again, I am showing you. So here, what will happen? We are applying Snell's law at a condition that it is equal to critical angle. So the first medium is n1, second medium is n2. Okay. So this Snell's law, if you apply sin, okay, theta c, and the angle of refraction here it becomes 90 degree. So sin theta c by sin 90 equal to n2 by n1. That will be equation 5. Okay. Sin 91. So what will happen? Sin theta c equal to n2 by n1. You just find theta c equal to this. Equation 6. Okay. Now we'll go back to our equation 4. Okay, in equation 4 we will apply the same condition. Okay, when theta 1 equal to theta a and theta equal to theta c, the equation 4, now we can convert this. Okay, equation 4 like this. We can rewrite sin, instead of theta 1, put theta a equal to n1 1 minus sin square theta, instead of theta we put theta c to the power 1 by 2. Okay. Now you apply this sin theta c, okay, in this equation. 6 and 7. So what will happen? Sin theta A equal to n1 1 minus, instead of sin square theta C, okay, n2 by n1, so we can put n2 square by n1 square to the power 1 by 2. Okay, take this n1 inside. So sin theta A equal to n1 square, because we are taking into the bracket which is having root. So n1 square minus n2 square to the power 1 by 2. Now take this side. So theta A equal to sine inverse of n1 square minus n2 square to the power 1 by 2, okay, which is equal to acceptance angle. This for a half acceptance angle. And this is called numerical aperture. Okay. Now the cone angle is 2 theta A. Now we can write theta A equal to sine inverse of numerical aperture. Okay, so we have derived numerical aperture and which comes as a 12 mark question. And even one more terms we can add extra. Okay, we can relate relative refractive index and numerical aperture. So relative refractive index between two mediums then equal to n1 square minus n2 square by, this is a general formula for relative refractive index. So n1 square minus n2 square. See, numerical aperture value is n1 square minus n2 square to the power 2. So we can put here del equal to numerical aperture square by 2 n1 square. So numerical aperture equal to n1 into 2 relative refractive index to the power 1 by 2. This may be numericals, or in MCQ they may ask. So this is the derivation, a very simple derivation. Okay. So numerical aperture and acceptance angle, you can start deriving from this point. Okay. Okay guys, that's all.